Recently, design of electric scooter has commonly adopted brushless DC motors in place of brushed DC motors. This research develops a new anti-lock braking system based on a slip ratio estimator for ES utilizing the braking force generated by the BLDCM when electrical energy releases to the load, yielding an analogous effect of ABS control in gas engine vehicles. Comparing to mechanical ABS, the design possesses the advantages of rapid torque responses due to fast electrical actuating response. The electrical ABS is realized by associating with kinematic and short-circuit braking. A current controller is used to adjust the braking force, while the sliding mode control strategy is adopted to regulate the slip ratio for best road adhesion while braking. Real-world experiments have been conducted for function verification. When a vehicle is braking under critical conditions, such as it encounters with wet or slippery road surfaces, or mistakes committed by drivers, usually leads to wheel lock, making the vehicle out of control. Therefore, preventing wheel locking up during the emergent braking process is extremely important, and anti-lock braking system has become a standard feature in the modern vehicles. Regarding the ABS with advanced control technologies, there are various design approaches. Those can be used to improve the performance of ABS, such as sliding mode control, fuzzy logic control, adaptive control, genetic neural control, etc. The reason for adopting brushless DC motors in EVs lies in its superior characteristics in output power and longer lifespan over brushed DC motors. Parameterized modeling of ES is the preliminary step while considering the design of ES speed controller. The magic formula tire model is adopted here, which describes the relationship between the slip ratio and wheel friction force. In general, the vehicle's speed can be measured from the non-driving wheel or integration of the acceleration sensor. When the driven wheel of ES reaches the predefined speed threshold, the braking procedure works according to the following steps. Step 1. Acquire Hall sensor signals from the BLDC motor. Step 2. Estimate the slip ratio from the slip ratio estimator. Step 3. Calculate the ideal braking current from the sliding mode controller as the reference input to the PI current controller. Step 4. Determine the duty cycle of PWM from the DSP PI current controller according to the difference of feedback braking from the current sensor and reference currents. PI control command is generated via DSP's PWM function.